Good morning, all. Welcome. So to kick off our Centennial, our first speaker actually has withdrawn this morning. So we're going to have about 10 minutes of time for you all to brainstorm with the folks around you, all the exciting things about hydrology, looking back 100 years. And in about 10 minutes, we'll have a couple opening remarks, and then our first speaker will be Praveen Kumar as scheduled for 8:15. So thanks to the early risers, and sorry you're being penalized for being on time. All right. Good morning, all. Good morning to those just joining us. Our first talk of the day wasn't able to make it, so we've had just a touch of a late start. Before we will start on time with Praveen Kumar at 8:15. But before that, just a couple of announcements from various folks around our hydrology community regarding the Centennial. So, no, don't sit down, Jeff. Hit the stairs. So first, section president, or outgoing, when does the gavel pass?
Soon.
Soon.
Yeah.
Jeff McDonald.
Okay. Well, welcome everybody. I just wanted to say a couple of words regarding the Centennial. First, I want to thank Adam for chairing our Centennial Committee, and things really get into high gear for next year. And between now and next year's meeting, AGU is offering a grant incentive program. So you can apply for anywhere between $1,000 and $10,000 to support a Centennial activity. This could relate to a narratives project where you're perhaps doing an interview of looking back perhaps on what's been accomplished in your particular area of hydrology. There are opportunities with StoryCorps. You'll see some of that this week. There are Centennial-themed webinars that could be funded and hosted through AGU. So put your thinking caps on. EOS is after think pieces linking to Centennial, so work with your technical committees in that regard. Next year, we're thinking of infusing each and every session within the hydrology program. Of course, we'll have somewhere between 125 and 150 sessions, most likely, with two invited talks. One would be looking back on the last 100 years, and one would be looking forward the next 100 years. We'd like these invited talks, at least the forward-looking one, to be done by an early career scientist. This will allow us to infuse all of the talks with some Centennial activities, even if the session itself isn't Centennial themed. So be thinking about that if you're proposing sessions. And then lastly, and I'll turn it over to Martin, don't forget today, the Langbein Lecture and Awards celebration for our section starts at 4 o'clock. Please come to that from 4 till 6. And then starting at 6:30 is our annual business meeting. It's co-hosted with Causal. The beer and the food is free, and we promise not to run out of food this year. So come to that. The business meeting's at 6:30 at the Grand Hyatt Hotel, and you'll see that in the program as well. Thanks, Adam.
Yep. All right. Yeah, go ahead, Martin.
Okay, good. Hi, I'm Martin Clark. I'm the Editor-in-Chief for Water Resources Research. I wanted to say that as part of this session, WRR is going to be having a special issue on game changers in hydrology. We'll be putting that on the website early in the new year. That's something that everybody who's speaking here is, of course, welcome to submit to, and anybody else in the audience or in the community is welcome to submit to as part of our efforts to celebrate AGU Centennial. So looking forward to that. Good to see everybody here. Bye.
All right. So just by way of background and getting us started at just the right time, so the session today is we're focused on a slate of authors who have wanted to or agreed to reflect on 100 years of progress in the hydrologic sciences. You'll see that all of the technical committees from our section are represented here. So the technical committees provided sort of brainstorming and lists of folks that we worked from. And these are interspersed also with some people who contributed talks of things they wanted to share about advances over the course of the last 100 years. So hopefully what you'll see today is the breadth of what we're doing as hydrologists, but also a chance to reflect on and celebrate some of our successes and also look forward at what we think the next 100 years might bring. And so this is our in many ways a kickoff to a year of Centennial activities for the AGU and for our section. And so with that, our first talk will be from Praveen Kumar. Yeah, all right. Thanks for joining, everybody.
Good morning. So I was hoping the first talk would be by Eric, who would have given us a nice preview of what has happened over the last 100 years, at least in terms of the remote sensing. What I'm going to talk about is basically some developments that have been happening over the last decade, which give us some idea of what potentially we could do over the next several years to come. So this talk is envisioned as looking forward based on some things that have been developed, and I'd like to acknowledge my co-authors, Alison Goodwill and P.C. Jiang, who are very instrumental in helping us think about these issues. So I want to begin first, so where do I go? Okay, white keyboard. Going back about 150 years, in 1867, Maxwell basically challenged some of the prevailing thermodynamic ideas at that time in terms of entropy. And his idea was that if you have a chamber full of gas and you had a demon who was able to look at the velocities of each of these molecules and could open this trapdoor to only allow high-speed molecules in one direction and the low-speed molecules in the other direction, you could essentially create an energy gradient and extract work out of this. The bottom line is that by changing the configuration, you're not changing the entire energy state of this chamber, but you're basically creating work out of knowledge about something. So this particular argument then gives rise to the idea that the knowledge of velocities is a fundamentally different attribute than the velocities themselves. So, and this knowledge can be used to create an energy gradient and therefore work. So my argument is that this essentially formed the basis for a lot of what we do in information theory. Basically contesting this argument over the last 150 years has given rise to the idea of a bit, the foundations for information theory, and so forth. So the key idea I want to drive home at the beginning is that information is just not a statistical quantity, which we think of in terms of probability, but it is a fundamental physical quantity. And to argue that a little further, if it was a fundamental physical quantity, one should be able to convert information to energy in a net basis. So imagine basically pulling out of thin air knowledge about something and creating energy. And that seems infeasible. We convert energy to information all the time. That's what our computers are for. But converting information to energy is something which is really challenging to think about. So there have been a couple of papers in the last 2 years. This is in 2015, December, where folks created what they call it on-chip Maxwell's demon as an information-powered refrigerator. So on a net basis, converting information to something that you can extract work out of. A couple of months after that, there was another paper, which is photonic Maxwell's demon. So this is on-chip. This is with light. But basically, we are in an era where this concept of information being physical as a physical attribute can now be harnessed to do things. So why is it relevant to hydrology? In hydrology, we have been, or in water resource science, or most of our science, we have been dealing with essentially conservation laws of momentum, energy, mass, and so forth, but we haven't thought about information as an additional dimension. We have essentially thought of it as a statistical approach to doing things. But if it is a fundamental quantity, could we harness it to answer some questions? So the question I pose today is, how do we exploit information for the Earth's system, or the study of Earth's system, going all the way from analysis to prediction? But before we get on to that, I want us to think about Earth's system as a complex system. And the closest complex system we think about is our brain. It's known to be one of the most complex systems. And what we do to study the brain is basically we probe it. We put sensors around it, and we understand a whole suite of signals that come out of it. And these signals are analyzed to get to how the brain functions, how its different components function, or if there is any challenges associated with that. So it helps us understand the dynamics, it helps us understand coherence and breakdowns, and map functions to local structure in the brain. We do the same thing with the complex system. We put sense instruments out in Earth systems, and we create signals. So the question is, what do we do with these signals? Most of the time, we are pulling apart one single variable or two that meet our interests and analyze them. But this suite of signals, these are taken from this flux tower, which we have in Illinois, basically show the propagation of fluctuations that move through this system. An example is, suppose a cloud covers the sun, and immediately you can see the response on the leaf. The leaf temperature drops, which changes the turbulent boundary layer regime near the leaf, which changes the fluxes that are associated with that. So this fluctuation propagates through the system. Now, most of the time when we are in the laboratory, we try to create this in a controlled environment. The natural systems, there are no controls. These are essentially fluctuating on their own, either through external stimuli such as solar radiation, or internally generated fluctuations through nonlinear behavior. But the key here is that these fluctuations, which are propagating through these different components across different time scales, carry with them information that we can understand how they interact and how the system is composed. So the key idea here I'm going to focus on is the primacy of fluctuations. So most of the time when we do modeling, when we analyze system, we are essentially looking at dominant signals. And which basically means that we are low-pass filtering either the signal, or our models are essentially low-pass filters because they are designed to capture the dominant signals. But there is a lot more information that happens in nature, and small perturbations essentially propagate across these many, many components. So what I'm going to argue for is that this information is encoded in patterns of these fluctuations. And these patterns then elicit response from their interpreters. Most of the time, it's a natural system, or it could be human. So can we study the dynamics through the propagation of fluctuations? You flick something, see how that propagates, and then you understand the behavior of the system. In nature, this flicking is happening all the time. And so perhaps we could answer new types of questions which we are not answering before, such as feedback and causality. That takes us beyond the realm of correlation and principal component analysis and so forth. Interactions across multitude of variables. How do these variables basically interact and shape the dynamics? And even begin to understand how the whole is greater than the sum of the parts. The best example is our brain, which is basically a very complex system, and the whole which we see, we don't even understand how it arises. So perhaps we can start to get to those kind of questions. So this is a well-known formula for entropy. That's the foundation for information is rooted in basically probability distribution functions. So much as calculus is our domain for understanding deterministic system, probability distributions are the foundations for understanding fluctuations. So I don't want us to be thinking that this is essentially another form of looking at a system from a statistical or probabilistic way. What I'm trying to get to is basically that this is something different. This is something foundational, which we can perhaps exploit. And again, the mutual information is information that is shared between two variables. The key development came through the concept of transfer entropy. Basically, what it does is it helps us start looking at causality. And the causality is rooted in basically exploiting the temporal asymmetry. If the past influences the future, we may assume that that's a causal behavior and not the other way around. And so imagine if you have two signals, z of t and x of t, and we're trying to predict a value here. It has a certain amount of uncertainty. And if this uncertainty is reduced because of the knowledge of its past, then this is the yellow is the remaining uncertainty, and this is what is called the mutual information. Now, if x of t further reduces its uncertainty, then this quantity here is what is called the transfer entropy. So this is the amount of information that x of t is imparting to the reduction of x of t which is not contained in, or z of t, which is not contained in its own history. And based on this, we can start talking about causality in a natural system. This is in the Granger sense for those who are familiar with that. So with that characterization, about a decade ago, we put out some study using flux tower data, where we looked at two different systems. This is a normal system, and this is a drought system, looking at eco-hydrologic dynamics of a crop. And what we found was that essentially on a healthy system, there is a very deep interaction that is happening across the different components that shape this particular environment. But during the drought system, there is a disconnection that happens. So the connectivity of the dynamic connectivity that exists breaks down. And all this is basically coming directly from the analysis of data, nothing of models, right? So this allows us to basically think about this kind of analysis, that it can reveal internal dependencies between components of a system. So I identify propagation of fluctuations between variables to expose dynamical connectivity. It can reveal coherent subsystems or sub-network of organizations, as you can see in these two conceptual diagrams. And it can reveal different functional modalities, droughts, or a healthy system, or very wet system, or any number of systems depending on the context. So from this very, very simple analysis, with the basically thinking of information as a way that these systems are communicating with each other, we are able to discern whether there is inherent modalities that exist in this system. So this happens for two variables. Now we can take this story further, and we can think of three variables. So last time, basically, there was a circle here. If we can think of that as a third variable, then we can think of how two variables, S2 and S1, source 1 and source 2, affect a target. Now, when these guys interact, basically we get four ways in which these systems can interact with each other. So this source can provide some unique information to this target. This source can provide some unique information to this target. These two sources may have some redundant information that is shared with the target, but together they may create some synergistic behavior which would otherwise not be possible if one of them was not present. So it is now possible mathematically to actually take the signal and break down this interaction into four different components. So think about it as unique from two sources, each of those two sources redundant and synergistic. So just to illustrate this idea, we used some weather variables, so radiation, relative humidity, air temperature, leaf wetness, wind speed, precipitation, all at 1 minute resolution. So pretty fast time scale dynamics. And so as an illustration, I'm going to just show you how two variables, air temperature and wind speed, we know that they affect relative humidity, right? I mean, we know the governing equations, but we can plot the fluctuations of these quantities over time. And so this is plotted over a 3-day period. And basically, there is a lot of information in there. There's a lot of details in there. And we can then break this down in these windows. So we basically had windows from midnight to sunrise, sunrise to midday, midday to sunset, and sunset to midnight. And you can analyze them. And what you do see is essentially there are some periods of time where basically air temperature pretty much determines the state of the relative humidity. But there are other times where all these four components start to play a role in determining how these two variables interact to create relative humidity. What you find here is there is a lot of redundancy between wind speed and air temperature, and less of the synergistic information. And so here you start seeing the synergistic information build up, redundancy go down, and then you have the unique components. So with this approach, it is possible to analyze this system. Okay, can we give me 2 minutes? Okay. And create a network of interactions. And with this network, we can pretty much begin to understand how the dynamics may be different across dry and wet systems. So, and we can even go further. We can start looking at basically how the time series structure itself will allow us to predict a particular target. So we've coined the term what we call a causal history, and basically understand how the causal history, the immediate and the distant, and we can characterize this as a function of tau. So tau can go from 1 down to n, and see how it varies, right? So how much information is coming to this target based on the history. And so we looked at some fractal time series, and what we see is basically that over time, this distant over the total information is persistent, which should be the case for 1 upon f kind of a dynamics. But we can break it down into immediate and distant, and so I won't go into the details of this. So the bottom line is this. So we can use this approach to develop progressively deeper exploration of information flow, and I talked about 3: transfer entropy, shared information, and causal history. When we're trying to do predictions, our goal is essentially to capture model dynamics that is isomorphic to natural dynamics. And by understanding the natural dynamics much deeper, we can perhaps do much better in model dynamics. So that's a question that remains. So we're essentially going towards a world where we will have sensors all over the place to measure everything. So this density of sensors should be able to tell us what is going on in this environment in much more detail than we are possibly able to comprehend and analyze and predict. So I think we can start developing these tools to understand our natural environment, our coupled human natural environment, for better prediction. Thank you.
So we're going to hold questions to keep on track and ask Praveen to stick around for the break. All right. And oh no, what do I do? You.
Full screen mode.
Full screen mode. Lovely.
Then we have to pause it, I think, because otherwise it starts running
Okay.
itself.
Oh no. All right. You drive.
No, I think it works. Thank you.
Go ahead.
Good morning. My name is Lieke Melse, and I'm presenting work today I did together with Nance Dor on legacy versus adequacy in hydrological model selection. So we all know that there's plenty of hydrological models around, and we also know that different models will lead to different results. So basically, selecting the right model for your research question will influence the conclusions of your study, so it's a very important step. So what we wanted to investigate is what actually drives this model selection. And for that, we defined 2 different hypotheses. One, adequacy. Adequacy basically relates to the research question. So you select your model, for example, based on the variable of interest for your research question, particular temporal or spatial scales that you're interested in, or specific landscape characteristics from the catchment you're interested in. Another hypothesis that we tested is that legacy is actually driving hydrological model selection. And legacy is everything related to practicality, convenience, experience, habit, and perhaps even parental affection towards your model. So in order to investigate this, we did a bibliometric analysis. So we analyzed peer-reviewed papers. What we did is we selected 7 hydrological models, and we gave these hydrological models as search terms to Scopus. And this resulted in 1,529 papers that Scopus returned to us. Of course, Scopus can only search the title, the abstract, and the keyword, so the name of the model had to be mentioned in the title, the abstract, or the keywords. That's why our database is not complete, but at least it's a rather representative sample. That's what we expect. So 1,529 papers, where each paper uses at least one of these 7 models. Well, we downloaded these papers from Scopus, and then we analyzed the content of these papers. So this is an example of a paper in our database. What we did is extract the affiliation of the first author. So in that way, we know where the study was conducted. We extracted the country of application. So this particular study was conducted in Australia. Specific landscape characteristics, such as ephemeral in this study. And we also looked for the variable of interest, the spatial scale of application, and the temporal scale of application. Of course, not all attributes were mentioned for all databases, so each attribute is a subset from our total database. So doing this for our 1,529 papers, we can actually make a map of where particular models are applied and also the country of application. So where were they used and where were they applied? Oh yeah, and of course we also had to do a manual check, because what you see here is that one of the co-authors is from Victoria, Australia, and they luckily used the VIC model, so this one works. But not everyone from Victoria, Australia uses VIC, so we really had to manually check all attributes of our database. So this is an example of maps that we could create with our data. What you see here is a map of countries where the variable infiltration capacity model is used. It's based on 309 papers, the data. We had 499 papers of VIC in our database, so 190 papers didn't mention a country of application. What you see is that VIC is particularly popular in the US and China, and that most studies conducted in these countries are also applied in these countries. So that's what the circular arrow is indicating. So we see a clear spatial preference for VIC use. If we look for other models, for example, top model and HPV, which were developed in Europe, we see that they're also more popular in Europe. So what we see here basically is a geography of science. We see that the way science is conducted is place-bound. Different models are used at different locations. Of course, that still doesn't explain what's driving this hydrological model selection, because as hydrologists, we are of course inspired by our environment. So it can be that some models are more appropriate at some locations. But it can also be that people just tend to use the model that they tend to use. So that's what we investigate next. Was it adequacy or not? One of the things we looked at is the variable of interest. What you see here is that all 7 models were used for studies that were interested in water resources. What you also see is that 5 out of 7 models were used for flood studies and 6 out of 7 models were used for drought studies. So basically the variable of interest isn't really explaining which model would be used for a particular study. Also, the temporal scale doesn't reveal any clear patterns. All 7 models are used for prediction, almost all models are used for climate change studies, and also almost all models are used for forecasting. So also the temporal scale is not a clear discriminator to use a particular kind of model. Also, the landscape and the spatial scale don't really show clear patterns. We see that all models are used in arid regions, but also almost all models are used in alpine regions. We see that all models are used regionally, almost all models are used globally. So what we see here is that these 7 models are basically used as models of everywhere and everything. And there is really not clear proof that adequacy is actually driving hydrological model selection. Our data doesn't support this hypothesis. If we look at legacy, however, what you see here is 10 different institutes and the fraction of publications with a particular model. And in white, you see the number of papers in our database. So for example, the University of Washington, Seattle has 53 papers in our database, and 92% of those papers used the variable infiltration capacity model, and the other 8% was Sacramento. This is what we defined as model attachment. So the percentage of papers used by each institute with a particular model. And if we explore this model attachment a little bit more, and we average out the average model attachment for each institute with at least 5 papers, this is the number that we come up with. This basically means in 74% of the cases, we could correctly predict which model was used only based on the affiliation of the first author. So this basically puts more perspective on the legacy explanation for a hydrological model selection rather than the adequacy explanation. So it seems that model selection is mainly driven by legacy rather than adequacy. Of course, this is a good moment for us hydrological modelers to do some self-reflection and to wonder, why is hydrological model selection mainly driven by legacy? Well, there are some very good reasons why we do it this way, and which actually is a good reason to do it this way. One is experience, of course. If you use a model you have experience with, this is very valuable. Experience is a very valuable asset in science. You can directly recognize suspicious results, you know how to handle certain errors, you know how the code looks like, so you can adapt the code if necessary. So experience is a very good reason to use legacy in model selection, because this experience really is valuable. Another point is, of course, modeling ecosystems. The model itself is just one thing, but we all have our scripts to create input files, we have our scripts to analyze output files, and we put a lot of time and effort in setting up this ecosystem around the model, and it would take a big investment to switch to another model for another research question. So this whole ecosystem is actually growing and sustaining this system. Another point that we know from literature is that there's a conventional approach bias. So reviewers, both from manuscripts but also from grant applications, have a tendency to prefer approaches that they are familiar with. So this actually sustains the whole legacy theory in our hydrological model. Question is, of course, is it a problem that legacy is driving hydrological model selection? Or is it just okay that we do it this way because this experience is so valuable? We've been thinking about it, and we think that there's a few opportunities that we miss. First of all, we're modelers, we're not stupid. Legacy might drive model selection, but of course a model has to have some adequacy as well. We're not going to present results with negative Nashut cliffs. Question is, however, if the model that we use is the most adequate model that's around. And that's what we don't know, because we simply use it because we're familiar to use it. And in order to know if your model is the most adequate model around, actually you need model into comparisons. You all know it takes a lot of time to set up a model into comparison, and it's very difficult to pinpoint and explain the exact differences in model into comparisons. So yeah, there is a missed opportunity here by having legacy driving model selection. Another point is that we invest a lot of time and money, perhaps, in the parallel development of the same kind of models. So there's a lot of models around, all having the same degree day method implemented. Many different people have invested time in implementing the same parameterization. And if one person improves it slightly, no one else is actually gaining this extra knowledge. So we lose time and money here in parallel development without really increasing our understanding. So there are some missed opportunities here, we think, when legacy drives model selection. So what we would propose to do is actually to move from flexible models to modular modeling frameworks. So most models nowadays are already a little bit flexible. You can turn off certain features or turn on certain parameterizations. But what we define as modular modeling frameworks, it means that several modules are available for the main structural elements, and that the architecture of the frameworks enables the addition of new modules. So why do we think that MMFs actually could resolve this issue? First of all, because you can easily switch among model structures. So you can have set up your whole model ecosystem around a modular modeling framework. It basically means that your ecosystem still works, but that you can conduct your own model into comparison. So you have more models at your disposal. Second, because you can conduct controlled experiments, you can replace one parameterization with another, and then you can really pinpoint what explains the differences between your model, and in that way select the right model for your research question. And third, because you can contribute to modularity. So in this way, we can overcome this parallel development, which is actually a waste of resources for model development. So we really think that MMFs can provide some answers in this whole legacy debate. Point is, of course, that they've been around for quite a while already, for at least 20 years, and they never really took off. One reason is, of course, because of this whole legacy prevalence. So we tend to use the model that we have most experience with. So we don't really want to switch to another model, also not a modular modeling framework. But another point is, of course, that modular modeling frameworks can be pretty challenging to work with technically. So there's really something we should discuss here, like, should we move towards this way of modeling, or should we stick to our legacy and everyone having their own model, which they like best? So we think that MMFs can provide guidance for model selection, and in that way actually increase the role of adequacy in model selection during your modeling procedure. And therefore we think that we should think about training a new generation of hydrologists actually to do their own model into comparison before choosing a model for their research questions. So that's the result of our bibliometric analysis. Thanks a lot.
Great, and we've got time for a question or two. Sure, loudly.
Thank you very much, Lika, for this enlightening presentation. I was wondering, do you think there is a difference in this legacy effect between models for which the code is openly available and models for which that is not available?
Perhaps there's a difference, of course, because if the code is closed, obviously it will only remain within that institute. So yeah, probably there is. Most of the models we investigated, though, have public codes available. Yeah.
One more quick question, if there is one.
The idea of moving to modular models, you actually lose something from parallel model development based on reading different assumptions and structures?
Well, that's the positive thing about parallel development is, of course, the pluriformity, so different approaches. So I really think we should stimulate trying different ways of modeling, and we really shouldn't think that one modular model framework is able to replace all models that are around right now. So what we actually advocate is, okay, we will have modular frameworks, but probably we'll have many of those as well. But it would at least slightly increase the role of adequacy in model selection. But of course, it's a complex system. There's a lot of ways to describe this system. So, well, I don't think there's one model that can do everything. Sure not. No.
Thank you.
Thank you.
All right. Our next speaker is Naomi Tague, and she is here to talk to us today about that green leafy stuff in our hydrological models. I don't know how to start this.
I'll do it. It seems that we're starting with the end of my presentation.
Oh, are we?
Yes, hang on. Let me go back to the beginning.
Yeah, in a centennial session, we want to start 100 years ago or so.
Wait, how can I get back to the beginning? I don't have a mouse.
What if we push the up arrow a bunch? All right.
Oh, I'll just do it the hard way.
But then how do we?
How come I can't scroll up? Oh, there's my scroll bar. There it is. Hello, scroll bar. Okay, you guys get to see my entire talk. Slowly, but this is really weird. Okay. Hello. Okay, so it's a challenge to give an overview of eco-hydrology in 15 minutes, but I thought at least I'd start with a definition, right? And this is a definition from a paper by Rodriguez Iturbe, which really says that the science of eco-hydrology is looking at how hydrology controls the patterns that ecological patterns that we see. Now, as an eco-hydrology modeler, I kind of unpack that a little because we care about two different things. We care about how water supply impacts vegetation function, its structure, its biogeochemical cycling. On the other hand, we also care about how vegetation mucks with the water that we use, how it affects stream flow, how it affects groundwater recharge, right? And then we also want to know something about how our management of vegetation affects both of those things. So if you go back in the history of how the eco is put in hydrologic models, and this is really still true today, is that we started by taking the structure of above ground vegetation, often through things like leaf area index, and looked at how those things affect evapotranspiration estimates from something like the Penman-Monteith equation. So how does vegetation affect radiation absorption? How does it affect the way in which we interact with the atmosphere, the fluxes of how easily water can be moved into the atmosphere? And then how do stomats control that flux of water? And I'll point out that way back in the 1980s, people like Steve Running were taking remote sensing images of LAI and linking those with models of evapotranspiration and photosynthesis, and showing us that the pattern of vegetation mattered for those fluxes. And within a couple of years after that, early 1990s, they were combining that with spatially distributed models, in this case, top model, to show that the redistribution of water combined with the vegetation structure affects evapotranspiration fluxes, particularly during dry periods, right? Early on in the 90s, we also had models. These models started to grow vegetation by linking them with carbon cycling models. So what we were able to do then is say, well, how does the recovery of vegetation or the change in vegetation structure with climate affect stream flow. Here using topog, for example, to look at the decline in stream flow as a eucalyptus plantation recovers. So in the last couple of decades, we've really matured in our ability to model this combination of grow and flow. There's a really nice review by Simone Fatihi in Water that covers the evolution of these flow and grow models. And yeah, we've made big advances, right? In terms of radiation, we can separate the effect of sunlit and shaded leaves. We've included the nitrogen cycle as another limit on growth. We've done better estimates of carbon cycling. We allocate carbon to roots, so we can say something about how water availability changes as vegetation grows, right? We've even gone so far as to link not just models of flow and grow, but actually to bring in coupled models of disturbance. Disturbances, things like fire or water stress mortality, which are related to hydrology, then change the vegetation structure, and then therefore will have subsequent impacts on the eco-hydrology, right? So I can give you, there are many examples now of these types of models. Here's an example of output from a model that couples a fire model with a dynamic global vegetation model that of course includes a representation, at least of vertical hydrology, and is able to predict fire return intervals distributed over the globe. So, okay, we have coupled models of flow and grow and disturbance. Are we done? Have we reached the pinnacle of eco-hydrology? What's missing, right? Well, Rodrigo Soturbe gives us a hint as to what's missing. Well, there are two challenges. One is that the controlling mechanisms in all of these processes changes with scale. So how you represent those underlying mechanisms has to change with scale. The other big problem is that ecophysiology characteristics and pedology, which as a hydrologist I would interpret it as storage and drainage parameters. These things are highly spatially heterogeneous. They also vary in terms of time. So we're still in this era of solving the scaling and parameterization problem. And now I'll point out, you know, hydrologists, we've actually spent a lot of time thinking about spatial heterogeneity in soil parameters. We sometimes forget that heterogeneity in ecophysiology parameters is just as important. Just to give you a sense of why this is a big number, here's just a single paper. It's some field measurements that show vegetation water use in a not water limited environment in the same place. And the different symbols show you the effect of different species, even for the same, say, diameter or breast height or the same above ground biomass, right? You have substantially different values of water use, right? So species matter. We haven't solved the scaling issue either. I'm pointing out to a new paper, hot off the presses, that Yin Fang led. She brought a bunch of people together in the hydrology community to provide insight into how we're going to do lateral redistribution for large-scale models, right? The vegetation models, the hydrology models that are incorporated into GCMs, right? This is a brand new paper. So I think we have to acknowledge that, yes, we're still in the era of solving the scaling and parameterization problem. But what I'd like to posit is that I think we should move into a new era. Not that we've solved that, but I think what should structure our thinking going forward, maybe, is using models and thinking about models as something, as tools to reveal what is hidden. And why do I say that? Because we're entering into the big data era. Well, we're already there. And what does that mean? We have a wealth of new information. We have new remote sensing imagery at spatial and temporal and spectral resolutions that we've never had before, and we can put them on drones. We have new isotope measurements that are increasingly easier to collect and analyze. We have all this big data. What we should think about eco-hydrology models as doing is helping us understand that data, using them to interpret the meaning, understanding the mechanisms that are implied in that data, right? So let me give you an example of what I mean. So in the US, during a recent drought, we had a huge mortality event. And an interesting question then is, well, why do some trees die and some don't? And people have used new remote sensing products, remote high spatial and spectral resolution products that can tell you something about canopy leaf water content, right? And they can correlate those with things like topography or species distribution. But what an eco-hydrology model should be able to do is tell you why topography controls this spatial pattern. And if you can do that, then you're better able to say something about, well, what would these patterns look like if we had a different type of drought, right? What if the drought was 5 years instead of 3 years? What if it was warmer, right? A related question is what happens when, to the water cycle, when these types of mortality events happen, or when we go out and directly thin forests. And if you look at field data, it's kind of all over the place, right? Some people predict evapotranspiration goes up, some people predict it goes down. We can use models to try to understand what are those underlying mechanisms that lead to that observed heterogeneity. Here's an example from my own work where we ran a model to say, what happens to the change in ET after a disturbance like that and recovery? And we differentiated the effect of assumptions about how well neighboring trees share water, how entwined are their roots. And we can see that effect, shown in the difference between pink and gray here, is big relative to the effect of climate variability. Our models can help us think about, tease out those different underlying mechanisms. But what makes this really interesting is if we can then link this with new ecophysiology measurements. Something like, here's a paper from Tamir Klein who's using labeled carbon to actually quantify the extent to which neighboring trees share resources. We can do the same thing with new theories that are emerging from measurements in hill slope hydrology. Jeff McDonald's and others have been talking a lot about this idea of two water worlds, which basically from isotope data have shown that the storages that trees or vegetation use are different from the storages that feed stream flow. That's great, but we need an eco-hydrology model to say, well, what does that mean for what's going to happen under drought? What does that mean for vegetation, water use, or stream flow under a wide range of different conditions? So what I'm calling for isn't really that new. People have written about behavioral modeling, using modeling for hypothesis testing before. But what I'm kind of pushing for is more of an emphasis on really using models not so much for prediction, but for understanding these new ubiquitous data sets, right? And combining that with the knowledge that we've already embedded in these models. From the last talk, you can see we've spent years developing these model structures, right? Combining that embedded knowledge with this new understanding that we're getting from data. But in order for that to work, we have to think about revelation in another way. We have to be able to reveal what's hidden in these models. And we've done an incredibly poor job of doing that, right? To understand what's in a model like RESIS, like top model, like SWOT, CLM, you have to go through decades of papers or crawl through the code. I myself learned BioBGC by crawling through C code, but I don't recommend that. It's hard for field scientists to be using the models in the way I'm describing if they don't know what they're doing. And we really don't do a good job of showing that. And I think that's really where we need to move forward. So in my own work, I'm trying to do things like visualizing the results of hydrologic models in ways that are more intuitive, right? For example, what we're doing here is we're taking the output of the model to show how things change at the landscape, but then letting the user pull out little cubes and showing this relationship between soil moisture and growth. But I don't really think that's enough. It's cute, it's getting us in the right direction, but it's not there. What I think we really need is something that animates conceptual models like this. This is the conceptual diagram that I use for a model that I'm architecture of RESIS, but all models have figures that look like this, right? And that's supposed to tell you how the model works, but it doesn't really, right? I want to know what equation are you using for interception? What theory are you using? Even if you were going to go to the modular modeling system, you still have a way of showing how you put the different modules together, right? In a way that really reveals what that structure was, right? And I think we have to find, and I think with new computing techniques we can do this. we have to find a way that this is automated, right? That whenever you code something, it creates the visual objects for you. Because if we don't know what's going on in these black boxes, I don't think we can use them in this way that we need to, this way of bringing understanding to these newly available data sets. So that's kind of my pitch on where eco-hydrology has been, right? We were doing flow and grow models back in the 80s, and we've gotten better at it. We still have issues with dealing with the heterogeneity. How do we parameterize things? Particularly for, I think, the eco side of these types of models, right? We still are dealing with issues of scaling. But I think going forward, it really is taking the years of embedded knowledge in these models and strategically and creatively thinking about how we combine them with these data sets to reveal what's hidden in these data sets and to reveal really what's hidden in the patterns and processes that we see in nature all around us. Thanks.
Time for one question as we switch speakers. All right. Thank you. Whoa. All right. Behave. Mouse. All right. Our next speaker is Dorta Tetzlaff, describing where we've come using water, using isotopes of all sorts, I should say, in catchment hydrology.
Okay, thank you, and thanks, Adam, for inviting me to speak at this session. I assume I'm the representative of the Catchment Hydrology Committee, which I shared for many years, so it's quite appropriate. So I would like to use my slot to talk about conservative tracers and stable isotopes, in particular in catchment hydrology, and just talk a bit about some of the past and present insights which we gained over the years from monitoring and modeling. But first of all, I would like to acknowledge my co-author, Chris Solutes. The work I'm talking about today is proper teamwork. So I assume not everyone in this audience today is an expert in tracer or isotope hydrology, so let me just give you a very brief introduction. Stable isotopes are so useful in hydrology because they are changing their signature just through mixing processes, no chemical reaction. So we can measure tracer input-output relationships in our systems to quantify water ages and to estimate storages in our systems. So we would measure a precipitation input signal and then an output signal after the water is moving through the landscape. And this output signal can be either measured in stream water, but also in soil water or groundwater. And both of these signals, the input and the output signal, are characterized by a large or strong seasonality with very depleted negative values during colder winter months and very enriched values during warmer summer months. But importantly, the output signal is usually much more damped than the input signal. And this damping really reflects the amount of stored water in the landscape the incoming precipitation is mixing with and interacting. And in addition, we can plot isotope in what's called the dual isotope space. And each of the different or specific landscape compartments are characterized by a specific isotopic signature. And we can use oxygen isotopes and deuterium isotopes, and the deuterium isotope is lighter than the oxygen, so it's more sensitive to evaporation processes. So this means any deviation or change in slope, what's called from the meteoric waterline, carries information of the sample on evaporation and fractionation processes. And similar, like Naomi was talking about, I found it difficult to summarize the major achievements in a 15 minutes talk. So I picked some of what I would view as benchmark tracer publication, going maybe back about 50 years. But all of these publications I'm showing show how it was increasingly acknowledged how important old or pre-event water is in systems because until then it was often assumed that it's the actual most recent precipitation which falls into a river is producing the flood hydrograph. So probably the first crucial paper in this regard is by Pinder and Jones, 69, who used chemical tracers to show the importance and contribution of old water to flood hydrographs. Then another paper by Martinek in 75, they used tritium as an isotope tracer to show how groundwater is contributing even during snowmelt. And then Sklash and Farfolden in 79 used different isotopic tracer to really show that groundwater can dominate the flood hydrograph. And following on from this Sklash and Farfolden paper, there have been an increasing number of studies on these topics, and many of them have been summarized in what I would view as the benchmark textbook on the topic, The Isotope Tracers in Catchment Hydrology, edited by Carol Kendall and Jeff McDonald. And this paper came out just 2 years before I started my PhD, so it's fair to say it was very influential, not just to my own work, but to everyone working in my team. And these early studies really began to influence the wider field of hydrology, and it became more and more apparent how useful tracers are to inform our models. And I think here a first key paper in terms of developing and using tracer-informed models was by Colin Neal and his colleagues in 1988. And they used chloride as a conservative tracer with a similar conservative behavior like isotopes to show that actually quite a small dynamic storage change was needed to simulate the discharge response correctly, but they failed to simulate the tracer response correctly using these assumptions. And the reason was that their Birken-Ness model they used was essentially still a rainfall runoff model which didn't incorporate mixing processes or didn't acknowledge the larger storage which is there in our landscape. So even if the discharge simulations were good, the model failed to characterize the storage, conceptualize the mixing in the landscape, and overall to represent flow paths and fluxes. But these studies still were incredibly important to really show this importance of old water and storage in our landscape. And I'm sure you have seen this graphic before, that we can visualize catchments like a bathtub. So our bath is relatively full. We would turn on the tap and it fills a bit further until then when a small storage change means that our tap is starting to spill. But this mainly reflects the spilling of the older water which was in the bathtub already before. And we can view in a similar way our catchment, a rainfall causes a small dynamic storage change which resides in a runoff response. But again, this mainly reflects the large storage which is stored in our catchment soils and groundwater which is displaced. And just to give you an idea about the scale of this total storage, this plot shows an example from an upland catchment where we constrained the storage by using geophysics techniques and also extensive tracer studies. And in the context of longer-term total catchment storage, and this is not even scaled, and just about 25% of this total catchment storage is shown, you hopefully see how much larger this total storage is in our catchments, about 3 orders of magnitude larger than the daily stream flow variations which we see here on the top. So in addition, it's also not long ago that it was actually very expensive to analyze an individual tracer sample. So we are talking about $15 to $20 per sample. And it's just relatively recent that these novel technologies revolutionized the field. We can use now these laser analyzers to build up long-term tracer time series at high temporal and spatial resolution. And here you see an example of, I would say, quite a unique long-term tracer time series of daily isotopes measured in precipitation on the top and stream water on the bottom measured in the Brundtland Burn experimental catchment in Scotland. And going back to the initial tracer-informed models by Colin Neal, based on this, more conceptual models, lump models developed, and they evolved into spatially distributed tracer-informed or tracer-aided models, which then really incorporated mixing processes in the catchment and also larger storages in our soils and groundwater. So here we see an example of the model STAR, a spatially distributed tracer-aided model we developed for our Brundtland Burn catchment in Scotland. And these kind of models allow us now to simulate discharge dynamics, stream water isotope dynamics, and estimate water ages. And these show quite nicely how variable these water ages are, ranging from a few years during periods when we have low flow situations to just a few months during periods when discharge is high. And we can use these kind of models then to investigate the spatial variability and its temporal dynamics in our runoff generation processes in our water ages. So you see on the upper plot the ages, and the yellower reddish colors reflecting older ages when runoff rates are low. And then when we move towards higher runoff rates, our ages become much younger. And these insights are only possible because these tracer-aided models are calibrated not just on discharge but on the isotopes as well. So just to summarize briefly here, we can use conservative tracers like isotopes to estimate water ages, to estimate the total storage in our landscape, and overall use tracers as diagnostic of different model states. And a lot of these experimental studies were conducted and then generalized really nicely by work by Scott Juchecko, Jim Kirchner, and co-authors. And they showed that the world's rivers are characterized by a high proportion of young water during high flows, and that aquifers are dominated by older water which reaches the stream during low flows. And subsequent work of this team has shown that very old water and very deep aquifers is often disconnected from our surface waters. There have been many more studies, and apologies to everyone in the audience whose paper is not listed here, but overall we have had a development from simple lumped conceptual models which evolved from simple convolution integral approaches towards the seminal paper by Jim Kirchner on spectral analysis, and then more recently, more probabilistic approaches using storage selection functions to estimate water ages. And just moving to the final part of my talk, and I'm really grateful to Naomi who's setting the scene so nicely. It is, at least in the blue water community, relatively recent that it is acknowledged how dynamic and central the role of vegetation is in water partitioning in the landscape, and in particular how vegetation can influence the water ages of blue water fluxes. So recently, and again Naomi referred to this, the focus has shifted that we are trying to understand the isotopic transformation of eco-hydrological fluxes while water is moving through the soil, plant, atmosphere continuum, and we are trying to understand where in the landscape water mixing processes are occurring and what the ages are, not just of stream water, but of soil water, in particular of these green water fluxes like transpiration and evaporation. Again, there have been many detailed experimental studies, but a very nice paper by Stephen Good et al. They showed again the importance of vegetation at the global scale using isotope and remote sensing data, and showing how important transpiration as one of the biggest fluxes back in the atmosphere is, accounting for about 64% of ET globally. Also showing how vegetation influences the 27% of ET which we lose through interception losses. And overall, they have shown that transpiration fluxes are much larger than the annual runoff of all the surface water or the surface runoff of all the world's river combined. And with this in mind, the recent development is now, and again, going along what Naomi was talking about, trying to develop tracer-based, physically based eco-hydrological models. By this I mean that we incorporate tracers into our eco-hydrological model to really follow the transformation, the isotopic transformation while water is moving through this soil-plant-atmosphere interface, and incorporating the complexity of these models. This model is a model Eco-ISO, which we developed based on the Eco model. This is maybe an example. The Eco model was developed by Marco Maneta, University of Montana, But we use this in Scotland to develop our tracer-aided eco-hydrological model. And just to show you an example how this looks, we can use these tracer-aided eco-hydrological models to simulate isotopic dynamics across different eco-hydrological units and estimate the ages of these different eco-hydrological fluxes. So we see here the isotope dynamics of a freely draining hill slope soil, a wet valley bottom soil. We can simulate the isotope dynamics in different groundwaters across the catchment, and then also the isotope dynamics in our plant water use. So to summarize, I hope in this short presentation I could show that tracers, isotopes in particular, really develop from a specialized subfield to a major data source for innovation in hydrology. This development was particularly driven by the event of increasingly cheap and flexible analytical tools like these laser analyzers I was talking about. We can use tracers to test hypotheses about complex multi-scale hydrological processes in terms of mixing interactions between various stores, fluxes, and ages. They are an important mean to help calibration and testing of our hydrological models, and the insights we gain from our empirical and modeling experiments are often surprising. For example, we can quantify the difference between the celerity of the rainfall runoff response and the actual travel time velocity. Ever more detailed study increase our understanding of plant-soil interactions and human impacts on water partitioning. And I think there's still clear scope, and again to echo Naomi's talk, for further development of these eco-hydrological tracer-aided models. So I hope most of you can agree that it's very likely that tracers will be an increasingly important field also in AGU's second century. Thank you.
So we'll have to hold questions for the break to stay on track. Thank you. All right. So our next speaker of the series is David Hanna. And so building on the increasing resolution we've seen in water cycles and how we're representing them and measuring them, David's going to talk to us about the water cycle, how we conceptualize it, and how this should look in the next 100 years.
Thanks, Adam. So good morning, I'm David Hanna from the University of Birmingham in the UK, and today I'm going to present the outcomes of an international research effort that was coordinated by Ben Abbott at Brigham Young University, and which began back in 2015 as part of discussions in a European Union funded project about how we depict the hydrological cycle. And this led us to analysing 464 water cycle diagrams, based upon which we've proposed a water cycle for the Anthropocene, which seeks to integrate human interactions with the hydrosphere in water cycle diagrams, and more importantly, in turn our thinking about water-related issues. This research is a contribution to the UNESCO Chair in Water Science at University of Birmingham, and also University of Birmingham's Institute for Global Innovation. So the rationale for this work was that human use of water, climate change, and land conversion are causing a global water crisis, threatening billions of people and many ecosystems worldwide. Just to give you an idea of the scale of the issue, the combination of water uses is equivalent on a global basis to about half the water transported between the ocean and the land. We know that climate change is accelerating the water cycle, and in some work we've done, we've identified how droughts will intensify up to 2100. And we know that 75% of the land surface that's ice-free has been markedly changed, and this impacts upon terrestrial hydrological processes, and we can identify in biomes which are anthropogenically influenced. So we'd suggest that that our ability to ensure and deal with the water crisis is dependent upon how we accurately depict some of these processes, because that drives our understanding of the drivers of change and the associated issues. So within hydrology, the hydrological cycle, the water cycle, is very much a central icon. It quantifies the stores and fluxes, both from empirical and modeling studies, and uses this information to explain how water moves around to researchers, policymakers, the public, and a range of other stakeholders. flaws in these diagrams really undermined the potential of using them as educational tools and as for management thinking. So on the right there, we've got a very proud sort of third grader showing her the water cycle, and although her dad was very proud of the artwork, he couldn't help but notice that the example of the hydrological cycle did not include the land surface at all. So, in this context, the aim of this research was to assess how the water cycle is conceptualized pictorially by researchers and by the public from different countries. So we looked at water cycles published in 12 different languages to consider whether this was an accurate depiction of our current knowledge and of the key global water crisis issues. We tested two hypotheses, the first of which was that the diverse viewpoints that created these diagrams would influence the focus, the detail, and the comprehensiveness of the diagrams, and that advances in our understanding of global hydrology and also a concerted effort to integrate humans into our perceptual models of the water cycle would improve the diagrams over time. So the methods that we adopted to do this were twofold. First of all, we used and synthesized data from 60 regional and global scale studies that quantified the different hydrological stores and fluxes to benchmark whether these depictions were accurate. And then we went on to analyze 464 diagrams of the water cycle drawn from the scientific literature and from a range of online sources covering 12 different languages. We classified these water cycle diagrams based upon the authors, the audience they were presented for, the biomes, whether they were 2 or 3D, their format, and the disciplinary area they were within. We noted within these diagrams the human impacts in terms of water use, land use change, and climate change. And we extracted 52 characteristics from the diagrams, and I just want to highlight 3 key types here. We pulled out the number, the magnitude, and the ratio of the different pools within the water cycle and the fluxes. We looked at the conservation of mass, and we looked at the representation of the ocean. So moving on to give you the results. What we found across analyzing all the diagrams that there were 4 main formats to which the water cycle was depicted. The vast majority were depicted as catchments. The next largest was on 2-dimensional hill slopes. Then 12% was schematic box and arrow diagrams, and 11% we regarded as site diagrams, which weren't quite hill slopes, but they didn't cover full catchments. We noted that in the vast majority, because of sort of right-handedness in the world, they went from left to right, and we took the diagrams and we greyscaled them and then looked at the distribution of pixels to look at what we might call common lineage, which is a polite way of saying plagiarism of water cycle diagrams, and found that there was remarkable similarity between them. 95% of the diagrams showed single river basins. Only 18% were quantitative, and across these we found 16 unique pools, unique hydrological stores with a mean per diagram of just over 6, and 27 unique fluxes with a mean per diagram of almost 10. To benchmark and to ground truth whether these water cycle diagrams are doing a good job of representing the pools and the flows of water, we took from the literature 60 state-of-the-art estimates of how much water was held within these, and these are plotted up here on the left for the size of the pools and on the right for the magnitude of the fluxes. And what I want you to just to take away is that they're ranked on a size order, and they run from smallest in the bottom left to largest in the top right. So what we then went on to do is to see if the size of these pools and flows were represented in the water cycle diagrams. When we look at the depiction of the pools of the stores, we noted that they weren't particularly well depicted in terms of their size. There was underestimation of the size of groundwater stores, of permafrost, of saline lakes, of soil moisture, and wetlands. And you remember that one of our hypotheses was to look and see if our representation had improved over time, and to also look between different audiences. And we found that there was no clear pattern in terms of differences over time and between the public and scientists. We also looked at the depiction of the water flows or fluxes. Here we can see there's a sort of better depiction, or in terms of the representativeness of the fluxes compared to the pools, but there was a marked underestimation of ocean circulation and also ocean precipitation across the piece. But again, no clear pattern in terms of changes over time or differences between the public and the scientific community. We also looked at different depictions for different disciplines. And what we can see here are different, in the top left, the space covered by the ocean, and then we've got different proportions of fluxes and precipitation, evaporation, and the ratio of the two. The grey lines show what we'd expect the value to be based upon the best empirical and model data. And we can see that there aren't very many differences between the different disciplines in terms of their estimates, but across the piece, the space taken up by the oceans on the diagrams was underestimated. The amount of precipitation and evaporation over land were overestimated, but by default, they got the ratio just about right. If we then went on to look at the depiction of landscapes and human interactions, this was really notable. But before doing that, it was worth noting that there was a clear underrepresentation of precipitation over the oceans, only included in 74% of diagrams. Across the piece, there was an overrepresentation of temperate ecosystems. Snow and ice-covered environments were picked up so frequently, for example. As I said before, single basin diagrams were the dominant type, and there's a lack of teleconnections, a lack of connectivity across basins. And all, apart from 1% of diagrams, gave no estimates of uncertainty in the pools or the fluxes. Most notably, however, was that in 85% of diagrams there was no evidence of human interactions. Although we did note a cultural difference between France and Germany doing a better job with a quarter of those diagrams having some note of people, but diagrams from the US, China, and Australia were quite poor in terms of identifying the role of people. We also looked across different disciplines to see whether any certain disciplinary areas were better at showing human interactions. We found that hydrologists, the natural sciences meteorologists, were amongst the best, but really surprisingly, given the importance of humans in much of their research, people working in land management and geography were actually quite poor at identifying people within water cycle diagrams. Only 2% of diagrams had anything to do with water pollution in them, and a very small proportion gave any indication of climate change. And really surprisingly, humans in the newer diagrams were less well represented than those in the older. We've also got to remember, in terms of thinking about human impact, that although we have arrows in the diagram representing flows that may relate, as in these two cases, to people, that all of that water is not available because the diagrams don't represent saline versus fresh water. The proportion of the different pools available for people is much smaller than they're depicted on the diagrams, and most diagrams didn't take any account of grey water or polluted water, which diminishes availability by between 30 and 50%. So we might want to go on then from there and ask, so why are these diagrams still wrong, and do we really care? Does it matter? So the critiques of these diagrams we recognize have been around since the diagrams started appearing in about the 1930s. One of the reasons is that they're perhaps inaccurate is that it's actually practically quite difficult to draw diagrams that show the relative sizes of the different pools and the different fluxes, because the pools vary in size by an order of magnitude of 6 and an order of magnitude of 5 for the fluxes. It may be that culturally we prefer natural environments, and they're aesthetically a nicer way to depict the water cycle. But there may also be a situation that relates to history and politics, where when these diagrams are emerging in the 1930s, this was at the same time as environmental hydrology was emerging, and there was a want to push away from engineering hydrology, so perhaps there was some deselection of humans within those diagrams. So I think, though, we've really moved on from when these diagrams were first produced, and we now know that humans really impact upon the water cycle, and that's much more extensive now, and it's better understood, so we really have no excuse. But you may still be thinking, well, why should we care? Well, if we take, for example, how these diagrams may be picked up in the context of water management, what they show is not that helpful. They show a lack of teleconnections, which may result in water managers thinking about single basin interventions. They have no representation, really, of the short and long-term dynamics of change. Yep. They break up water quantity and quality domains, and as a consequence, overestimate available water. And lastly, they very much focus on the supply side and overlook demand management. So, what can we draw from all of this? We can see from the water cycle diagrams that they're very much don't really pick up the human domination of the global water cycle, and that cascades on in terms of affecting our perception of the water crisis. From looking at the diagrams, we can see that there appears to be an abundance or an excess of freshwater resources available, which isn't true. the diagrams don't show the effects of climate change, and they don't particularly distinguish saline and polluted water. They almost unanimously underrepresent the aspects of the ocean, both in terms of size, circulation, and precipitation, and have no real feeling for teleconnection. They also don't represent multiple catchments, and dynamics are not included. And these flaws are prevalent across disciplines and through time. Therefore, there's a real need for a revised diagram, which I'm going to present now, and is broken up into 3 elements, and we propose as a water cycle for the Anthropocene. So our diagram, which represents the pools in the suite of 3, picks up many of the issues that have been omitted from other water cycle diagrams. It shows people, it shows pollution, it shows saline water, it represents the oceans more clearly, has multiple basins, as you can see, and represents teleconnections and includes non-temperate environments. This element of the diagram shows the water pools and also expresses the uncertainty in those based upon the range of estimates. We produced a water cycle diagram that shows the fluxes, the movement of water, and as well as in the yellow, including, if you like, the natural water cycle, we've been able to look at the human appropriation of water separated into blue, green, and grey water use. And lastly, we identified a water cycle diagram in which we picked out the human influences in terms of impacts upon climate, land cover, and upon water use, which picks up something to do with the dynamics, but also highlights the fact that we very much need to reintegrate humans into our thinking about water cycle diagrams as a critical first step in understanding and sustaining our what we might call socio-hydrological cycle, and getting people to think about how we move towards solving the water crisis. Thank you.
So we'll hold most questions, but as I switch this over, David, can you tell us where we get our hands on these diagrams for our classes next semester? Seriously?
Seriously?
Yeah.
Well, it depends upon the speed of the review process.
Ah, I see. All right. Thank you. All right. Our next speaker of the session is Pete Lokes, and we are taking these conceptual systems that David has inventoried and updated for us, and thinking about systems in a slightly different perspective of how we actually are operating them as a species on the planet. All right, I'll turn it over. Thank you.
Thank you, and whoever thought of inviting me, I appreciate that. Probably because I'm supposed to talk about the past as well as a little bit about the future, and they figured that I might be able to talk about the past anyway, okay? What I'd like to do is change, so I hit these things? Yeah, okay. I changed the title a little bit to talk about, instead of hydrologic systems, to talk about water resource systems, okay? Because you guys know a lot more about hydrology than I ever will, and I don't want to compete with that. So I'd like to do that. And assuming that at least one of you may not know too much about this systems analysis stuff, let me tell you what a system is, okay? A system is a bunch of components that are connected with each other in some interrelated way, and the whole scope of dealing with systems studies is that not to focus on each component or the links between them, but to focus on the whole system. So we have components in the system. My apologies for this is so elementary that you probably walk out. We have interactions between the components. We have inputs coming into the system, and we have the performance of the system that we're interested in. And usually we have more than one indicator of performance, and we're interested in the values of all those performances. For those of you that can recognize that diagram on the bottom, it's you have two objectives and various values of each objective. And it's been my experience in the real world is that the focus typically is on the frontier. In other words, which is the best solution on that red line that goes under the bottom of those points. because those are called efficient, and I've never seen a decision maker pick an efficient solution. So the others are good. The others are good and worthwhile. All right. So, but it's not these tools that we talk about, and very often we use jargon like optimization, and we're going to optimize everything. We don't do that at all because there's so much judgment involved in these models that we're dealing with. First of all, the boundary. What do we include in the system and what do we include outside the system? And what we include in the system depends a lot on the data we have available, the time we have available to do it, and the scope of the client that we're dealing with and what they can do and what they can't do and what they're interested in. And also we have a complexity issue. Somebody has stated that all models are wrong, but some are useful. Well, they're all wrong because they're not as complex as they should be, but the more complexity you add, the less they're useful. And so that's a dilemma that we have in the business, okay? So I think of hydrologic systems as what we've just been exposed to. Such a great talk we just had. So I think of natural water cycles and urban water cycles. Again, the water flows from the left to the right. And it's sort of what's happening in the nature. And a water resource system is the impact that we have of mucking up that natural system that we have and putting lots of infrastructure in it so that we can generate power and irrigate fields and provide water for ecosystems and navigate and so on. So that's a water resource system. And so the reason we do this is that we're interested in having, in serving multiple purposes and objectives with this water that we have to deal with. And all these systems deal with other systems. And of course now the interest is, how does the water resource system link with the energy system and the food system and the social and political systems? So here's a system. It's a conceptual model of a water resource system. It's got a lot of stuff in it, but not as much as it could have. But here's another system, and it's a water treatment plant, and that itself is a system. And people that are interested in designing and operating water treatment plants might not be interested in all the other things that we can do with water. And the same thing is true with wastewater systems. And if you don't think that's a system, there it is in New York City. That's a wastewater treatment system plant that's sitting in New York City. And I'd call that a very complex system that's worth analyzing. So I got introduced to it. I started my career in this field. It's not the first field I was in, but in this field in the early 60s, and my advisor gave me a book to read, and this book was the results of a Harvard book, but it was it followed the footsteps of guys like these that did water engineering. They wrote books and educated us on hydrology and hydraulics, sanitary engineering, and health impacts and so on. And that field is still alive and well, okay? There's still people writing books on that and still teaching courses in that, and that's important for the background of what we do, okay? And I understand that one of these books you can download into a cell phone, and when you don't have anything better to do, you can read chapters in water resources engineering. But when you get into water resource systems engineering, we're talking about combining that with economics and social objectives, much to the disgust of some of my good friends in hydrology who think that's heresy. And we're dealing with basin scales, multiple purposes, multiple objectives. We're using computers, and not that the others don't, not that all of you don't use computers, but in the old days that was sort of new, and dealing with something called algorithms. And it really changed the scope, I would argue, of water resources planning and management. And who did it? It's these guys, okay? Among others, for sure. But the Harvard Water Program that began in the 50s and went on into the 60s and a little bit in the 70s produced this book that I was supposed to read to start my education in water resource systems. And these are some of the authors of that book. And interestingly, we're talking now a lot about social hydrology and social impacts. The main author of this book is Arthur Moss, which is the first guy on the left. He's in the government department of Harvard. So it started out as a social issue. We had a lot of fun because in those days, part of the fun in doing this was to work with this new technology. And so some of us learned something about paper tapes, and I remember booting up a computer with paper tape. And then we had these IBM cards. And for those of you that don't know what an IBM card is, look at it. It's, this is on the left, okay, the middle one on the left. And the information on that card is in the holes, okay, not in what's not in the holes. And we had card punchers, and somebody's written that if you take all the data that Google has, 15 hexabytes, that's 15 to the 18th power of bytes, and put them on IBM cards and covered New England with those IBM cards, it would be 3 times higher than the Ice Age for that. I don't know where they got that, but that's what they said, okay? And another thing that's nothing to do with water, okay, but in 1953, there was an election, and Eisenhower was running against Stevenson. Anybody here at that time? Nobody, okay. So I can say anything I want. And it was the first time that a computer was used to predict the outcome. And the outcome was going to be obvious. I mean, there was no question about it. Eisenhower was a real hero. And so they showed on TV at that time pictures of the UNIVAC computer used to predict the outcome of the election. And what Mike Fearing, a Harvard professor, told me is that was a big fake. Because this is Walter Cronkite, by the way, in the picture, the one on the right is Walter Cronkite. And it was a big fake because, first of all, if a computer's grinding away something, there's nothing to see, right? It's a black box or whatever. So they had to show something, so they showed cards being sorted. That's a card sorter, okay? And what was really happening is in the back, behind a curtain, were people like Mike Fearing and other Harvard guys doing statistical and systems analysis tools to figure out from the poll data that were coming in who was going to win. And they would write it on an IBM card, type it up, and slip it into the card sorter so Cronkite could get out that card and say, the computer tells us that this is going to happen. That's what I was told, okay? Anyway, the field has progressed from the upper left was the design of water resource systems, very similar to this topic that I was asked to talk about. Hall and Dracup were pioneers out on the West Coast, and then from then on, a lot of books have been written describing better ways to do water resource systems. And it really has changed, and journal articles as well, and journals devoted practically to the field. It's changed the scope of water resources planning and management. But it's also enabled firms to make a living, okay? So there are firms out there applying water resource systems and surviving very well. Some of these people you might know, including Deltares and DHI over in Europe. So here's a water resource system. It's a hydrologic system that serves various purposes. And here's a social system, okay? And these are the two components that we talk about now of being in a water resource system. My apologies to those who have seen this diagram too many times. And our challenge, and it's been mentioned in this conference already, is that what influence does hydrology and water resource systems have on human social systems? Trying to understand that better, and we just heard that a while ago, and also the influence of social systems on hydrology. And we're not very good at modeling that yet. And I don't personally think it's going to be possible for us hydrologists, if you will, or water resource systems people to model human behavior. But there are people out there that are trying to do this. And if they do it, I think they'll get a Nobel Prize. And it's going to be a boring world if they do, right? I mean, after all, the nice thing about this world is we can't predict what's going to happen in the future. And so it makes it exciting, okay? There's various dimensions of water that makes water special. And I'm thinking when I saw this, that, air is also a big deal, right? If we didn't have it, it would not be a good life. And soil as well, where we get our food. But we don't make a big thing out of air and water in terms of religion and social and economic and political and moral, cultural things. But we do in water. And how do we incorporate that into our analyses? So bottom line, people are involved. And that makes life interesting. But people don't always have the same goals and objectives, and that also makes life interesting. Okay. Our challenge is to incorporate their goals and their experiences into our models so that we can better inform them of the consequences of what they might think they want to do to improve the situation with regard to water. So we need to understand and predict the relationships between humans and water. How does that influence political power structures? It's often been thought about here in Washington, at least a while ago, that we have 50 agencies in the US government, I'm told, that deal with water. And that's what you call inefficiency. So some people have thought about the idea of putting it all under one cabinet, the Department of Natural Resources or something like that. But it's never going to happen, right? We're going to remain inefficient. And the main reason is because of people and the power structure in Congress and so on. A big issue that we need to deal with, I would claim, is the communication. And it's good. Every session that we have in AGU, or every meeting that we have in AGU, some sessions are devoted to communicating our results to the policymakers. And that's still an issue, and that's still a big deal, okay? And I also think that we need to, we've done a lot to communicate with decision support systems and color graphics and interactive modeling to get humans involved, to get stakeholders involved in the planning and management decision-making process. But we've got a long way to go on that. Is that me? Is that 2 minutes to go? Whatever. Yeah. So, but here's and this takes a little more money than most of us have, okay? But this is a simulation that Navy pilots go through, and they're in the environment that they're simulating, and we need to get there. For those of us that are dealing with the interface between water resource systems and people, we need to develop better decision support systems so that we put the stakeholders in a simulated environment that they can experience what the consequences may be. And somehow understand that it's all a computer and it may not even be true, okay? But these guys think it's true, okay? They're by the way, that's fun. If you haven't done that, this is fun, okay? I should go back. Yeah, I'll tell you, do I have a minute? Okay. Wrap up quick, okay. I was in Delta Airlines has a simulator in Dulles, and they put me in a simulator once, and we were flying around Washington, and here's the Washington Monument sticking up in the ground. And I asked if I could fly through it, and the instructor said, go ahead. And I thought, well, that's going to be too easy. So I said, can I go upside down and fly through it? And he said, try it. And this is a 747, okay? So I turned it upside down and flew through the Washington Monument, and I'm here. Okay? Yeah. But the other thing is, wouldn't it be nice if we had models that didn't only analyze things and synthesize everything that we put in the model, but it would tell us something that we never thought of. In other words, we need, and it's been mentioned before by a previous speaker with regard to forests, I think, it would be nice if we could innovate and come up with a new idea that, I never thought of that. And I don't know how that's going to be done, but that would be a goal that I would think would be necessary. Okay, that's the challenge, all right? That's the conceptual model, and thank you very much for this. Okay.
All right, and as we get our last speaker of the morning session loaded up, just a reminder, we'll be back in this room after the break for another round of 8 talks from our speakers. Left and right arrows there. And our last speaker this morning is Gregory Hammer to talk to us about all of the data that we've collected and aggregated over the last 100 years.
Good morning, and
Good morning and thank you. I am actually a meteorologist, so I feel right at home in the AGU world, so thank you. And I work at NOAA's National Centers for Environmental Information, and we have the small task of archiving basically all the data that NOAA and its partners archive environmentally. We have, you can see each month we add about 166 terabytes of data. That'd be the capacity of 30,000 CD-ROMs. We currently have, and our data it's not just terrestrial. Our data goes from the ocean floor to the surface of the sun and everywhere in between. So we have massive amounts of data. So a lot of these models, even if you don't directly use NCI data, it's all in the models. That's where all that information comes from. And we are the country's chief environmental archive. And we have hundreds of years worth of data. If we were to put all of our data onto the latest, greatest iPhone out there, it would, and you stacked them up, it would stack up more than 6 kilometers, and which is 20 times the height of the Eiffel Tower, and that's how much data we're holding. And we're really glad we moved away from the paper archives to hold all that. Our data began modestly in the early days, obviously, just it was primarily ledgers and archives. This image, this is an actual image. This was the weather observations made by Benjamin Franklin in July 1776 in Philadelphia. He was a very proud man. He had just bought his first thermometer a few days before, and you can actually see, it's hard to see, but he was taking readings every couple hours and noting what the weather was. And so he was doing that in addition to some other things going on at that time. So, but the oldest data journal-wise that we have in our collection begins 1742 and goes up through from satellite and radar to just when I started speaking. So that's the amount of data we hold. Thomas Jefferson really kicked things off when he was president because he ordered the first U.S. survey of the coast. And Jefferson was also instrumental in, he thought that there ought to be a weather observer, particularly precipitation observer, in every county within the United States. And so that he's actually a forerunner of the National Weather Service's cooperative weather program, as well as the modern day citizen science project, CoCo-ROS, if you're familiar with that. As I said, we start from the ocean floor, but this is a little ocean surface. Prior to really World War II, buckets were literally lowered over the edge of the ship, water scooped up, and the temperature reading was made from there, and that's how they made that. Bottles and simple probes came about in the early 20th century. Starting about World War II is when the water temperature at the engine intake system of ships was begun. Today, Argo floats are the workhorses for taking the ocean's temperature for NOAA. There's almost 4,000 scattered around the world measuring temperature of our oceans, and they are, NOAA just notched its 2 millionth series of observations made by an Argo float. So that's how many there have been. And where I work, National Centers for Environmental Information archives the Argo float in the World Ocean Database that some of you may be familiar with. Mapping the seafloor. This is the way that things were done before. First was literally a stick was pushed down in to see where you hit bottom. This is in Alaska in the 1940s, and he's actually using lead weight on a string to do the measurements. One of my favorites actually here is a drag line, and there's a ship on this side, a ship on this side, some floating, some floats on top, lead weights at the bottom with wire connecting them, and the ships would move in the same direction, and if it snagged on an underwater object, they would be able to figure out the depth and just note that they snagged on something. So that was great for finding this. It's a rock in this case, but for shipwrecks or whatever. This one image up here is the first systematic measurement of the depth of the Gulf of Mexico. And this was done from 3,000 samples on the steamer ship Black, 1873 to 1875. So that's pretty advanced. So you're talking not quite 150 years ago. Today, seafloor mapping is done through things such as side scan sonar, single beam radar, multi-beam scanner. We archive all this, and there is a large crowdsourcing effort to map the entire ocean floor by 2030. The surface of Mars is much better mapped than our ocean floor, and that's a kind of an interesting thing. We house the International Hydrographic Organization Data Center for Digital Bathymetry. So this is kind of hard to see on this. Monitoring tsunamis. This is an autographic trace called a marygram. Mary not as in a lady's name, but as in word for ocean. And you can't quite see it on there, but this is a trace at a tide station, and so you're measuring the high and low tides, and also they were able to go. We recently salvaged and digitized 4 major tsunami events using this marygram data. And this information helps go into models to better predict and understand tsunami generation and propagation. That's how marygrams, and marygrams have been around since the 19th century, so it's a dedicated technique, but today we use the Drought buoy system, and there's 39 of them in the Pacific, North Atlantic, and Caribbean, and that stands for, because the government loves acronyms, Deep Ocean Assessing and Reporting of Tsunamis. That's what DART stands for, and it's even trademarked. Isn't that lovely? So, they also have bottom pressure recorders, and National Centers for Environmental Information archives the data from the bottom pressure recorders. The animation on the right side is a. I'll let you see that again because it only plays once there. These are copies of sunspot drawings made by Reverend Jonathan Fisher in Maine in the year 1816, and those in the weather or climate world know that 1816 was the year without a summer, as it was called in the Northern Hemisphere, and so Reverend Fisher's hypothesis was that, that the sunspots were affecting the temperature or causing it to cool, which is, as good a hypothesis as anything. Later on, we found out it was Mount Tambora in present-day Indonesia. But 200 years ago, here's an educated person making observations like that. Today, we use NCI archives the data from GOES and Discover, among other things, and they monitor the sun. GOES is about 22,000 miles above the Earth's surface in a geosynchronous orbit with the Earth, and Discover is at L1 or Lagrange point 1, 1 million miles above the Earth's surface, and it's our first-line defense in monitoring space weather. Data storage then, much like the last speaker, here's somebody actually using a punch card. Reel-to-reel tapes, a real fancy, probably an IBM early machine right there. And the National Centers for Environmental Information has stored, because we've been around in various formats, almost 70 years. We've used everything from punch cards, microfiche, microfilm, floppy diskettes, CD-ROMs, magnetic storage, computers, and now it's all big data and getting stored in the cloud. This shows just some of the server systems to date. Like I said, we have 38 petabytes of data, which includes a copy of the digital. There's a lot in non-digital format that we do not. And we have full-time archivists to help make sure that that data is saved not only for our use, but our children and our grandchildren's use as well. So that's my presentation. Thank you. Thank you.